Yes, students, as usual, let we take a follow-up of the previous learnings, then we will proceed. Last time, magnetic properties, those I discussed. I want to continue that issue, that topic. But before that, as a part of revision, the elements of the transition series from the periodic table that we have discussed, I want to know from you, what's the atomic number of silver?
47.
47.
Good, 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 good. What's the atomic number of gold?
79.
79.
Yes, confusion or correct?
79.
79. Correct.
What's the atomic number of copper?
29.
29.
29.
Yes. What's the atomic number of manganese?
25.
25.
What's the atomic number of molybdenum?
42.
42.
42.
Good, good. What's the atomic number of ruthenium? Ru?
44.
44.
Brilliant, brilliant. All your good. Okay, so about the labeling and the atomic number of transitions element, somewhat concept is clear to you. Then we started with the further understanding of these elements with various properties. In that, we discussed the oxidation state. Already you should know electronic configuration, and on the basis of electronic configuration, you understood the oxidation state. And in that oxidation state, there is one formula for minimum oxidation state. What's the formula?
Number of electrons in 4s.
Yes, number of electrons in 4s. And what's about maximum oxidation state?
Number of electron in 4s orbital plus number of electron unpaired in d orbital.
Number of unpaired electrons, very good, in d orbitals. That's a 3d orbital. It is especially for first transition series. So if I take example of chromium, then what's the minimum oxidation state for chromium? Minimum oxidation state.
1.
Yes, +1. And what's the maximum oxidation state for the chromium?
+6.
Plus
Very
6.
good. I want example of chromium where it is in +6 oxidation state. Yellow color.
K2Cr2O7.
K2Cr2O7. Potassium dichromate. It is orange in color. It is yellowish color is there. Absolutely answer is correct. But one more example I want.
K2CrO4.
Right. What's the name about that? K2CrO4 means
Sodium chromate.
potassium is there. Chromate, CrO4 -2. Very good, very good. All answers I am finding correct today. What is the color of its oxidation state that I discussed? Now I'm coming to the color. Color one sees is due to.
Absorption.
Right. And absorption is due to.
Excitation.
Excitation electron.
Good, very good. Excitation or transition of electron. Now these transitions are of different types. Which types of transitions are possible? Electron can move from which orbital to which orbital? Where to where?
DD transition.
Right, it's the one. I want second.
Metal to ligand.
Right, brilliant. I want third.
Ligand to metal.
Here to metal.
Right, good. So this DD transition, for that one example you can quote. Which example will you give for DD transition?
Ferric.
Ferric aqua complex you can take, or copper aqua complex you can take. Means in aqueous medium, how copper form the complex. Copper +2 I'm saying. Okay, good. For metal to ligand, example, metal should be in low oxidation state. Iron orthophenolphthalein complex, where iron Fe remains in what? The +2 oxidation state. And for ligand to metal, example, now I will not help you. I want answer from you. Ligand to metal, where metal is in high oxidation state, charge on metal will be large.
Mn+7.
Yeah, it is true, but I want example, compound I want. Compound of Mn+7.
KMnO4.
Right, KMnO4, potassium permanganate, or iron, if I consider iron in +3 oxidation state and its complex with thiocyanate. So total charge on complex is -3, or you can say ferroin indicator. When iron is in +3 oxidation state, it shows the reddish coloration. So these are the examples for the transition, types of the transitions. Few metal ions we discussed and their colors. What is the color of chromium +3?
Green.
Yes, color is green. Brilliant, brilliant. What is the color of Fe +3?
Yellow.
Yellow.
Yes, yellow. What is the color of scandium plus 3?
Colorless.
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 Good, good. It's a colorless. Which metal ion was there where I was confused and I committed mistake?
Titanium.
Titanium
Charge out there.
plus 4.
Titanium plus 4. What's the color? Actual answer.
Colorless.
Colorless.
Colorless. It's but I said wrongly. It is yellow or blue in color. That also you will remember. So these are the ways by which we can play with the concept and we will remember the things. Brilliant, brilliant. Now last question. Color of Mn plus 2.
Pale pink.
Pale pink.
Good. Pale pink. See, revision is important. Few could able to immediately answer. Few will say, yes, pale pink. I remember that. So it will take time. Now neurons are taking time to report. Why? Because you are not practiced. As you practice it, neurons will help you. So it is a game of patience. It's a game of practice. It's a game of revision. So now the things you know, if you do not revise, if you do not recall, then you will forget those. It is a bit natural. Nothing to worry. Next time, maybe memorization will be what early. But problem comes to the student. Student loses the hopes and do not what continue that. There is a problem. So therefore, what we did, revision process, we are what following. Now let us come to the today's point. That's magnetism, which already I started. I told you three types of magnetic materials are there. Which are those?
Dimagnetism.
Diamagnetism.
Yes. Next.
Paramagnetism.
Paramagnetism.
Yes.
Ferromagnetism.
Ferromagnetism.
These diamagnetic materials are repelled or attracted.
Repel.
Repulsion.
Paramagnetic materials are repelled or
Attract.
attracted.
Attracted.
Attracted, but weakly attracted. Ferromagnetic materials are
Strongly attracted.
strongly attracted. So weakly attraction that we understood from the concept, it moves from strong field to weak field. That's compound or material if it gets magnetized, no? So from strong field, you will try to go toward the weak field. So it has tendency to pass the few lines through it. While in case of ferromagnetic, if you bring that material to weak field, it will try to go to strong field. Automatically, it will move towards it will get some attraction towards what the strong field. It depends after all the strength of the magnet also. If magnet itself is of the low strength, then paramagnetic material will find at pole also, at end also will get attracted. But when it's considered strong, then that paramagnetic will say, in spite of the strong power, it is go to the weak power. It is enough for that. It depends on its tendency. This complete magnetism or magnetic properties are there due to one entity in the atom. What is that entity? Which we say as a tiny magnet. That entity is called. Is my question clear?
Repeat, sir.
There is one entity in the atom or ion or molecule. Because of this complete story is there. Because of this story of magnetism is there. What is that entity? Three letters are there in front of you.
Electron.
Right. Electrons or electron. Electron remains with two kinds of speed, motion. Because of that magnetism is there. One motion is called as spin motion and other motion called as orbital motion. And because of those motions, speed, velocity is a vector. It remains with direction. So spin also has one direction, maybe clockwise or anti-clockwise. So one electron is with the one spin. So how we represent the electron? We represent electron likewise. Say this spin is plus half spin. Then it will cause one kind of magnetism. If I consider other electron and its spin that we say as a minus half, it has other kind of magnetism. And what happens? Magnetism caused by this electron gets countered by other electron. Countered means opposed by other electron, or it will cancel. Magnetism due to one will get cancelled by other. So when cancelling remains, so net magnetism, that's a mu, will be equal to 0. And when that magnetism get cancelled, then we say that material is diamagnetic in nature. When electrons are paired, then those electrons have no tendency to get attracted towards the magnet. Since they do not allow the magnetic lines to pass through the material will experience repulsion, and that remains a property for diamagnetic material. So listen carefully now. If there is no unpaired electron Or if all electrons are paired, then compound or material will be, yes, complete the statement. If there is a no unpaired electron or all electrons are paired, then that compound element or material will be or ion will be
Diamagnetic.
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 diamagnetic. And if there remains any unpaired electron, any single unpaired electron, so then it can be paramagnetic. If less number of unpaired electron, paramagnetic. High level of paramagnetism is nothing but the ferromagnetism. So as a part of discussion, we will consider only two types of the magnetic material. One, diamagnetic, and second, paramagnetic. Diamagnetic means no unpaired electron, and paramagnetic means presence of unpaired electron. An extreme stage of paramagnetism we are understanding as ferromagnetism. Now with example we have to discuss. Before that, I told you magnetism is due to speed, and two types of speeds are there. Yes, which speeds are there for electron? Electron remains with two motions, two speeds. One speed is
Spin.
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 spin motion, and other is
Orbital.
Orbital.
brilliant. All you are brilliant. Very good, very good. Orbital. So because of these both speeds, magnetism should be there. But for the compounds, those we are discussing, those are the first transition series compound, or you can say second or transition series compounds, in which electrons do remain present in d orbital and outer. In elemental state, they can be in what the s orbital, but in ionic state, electrons will remain present in the d orbital. And electrons in d orbital, let it be the 3d orbital or 4d orbital or 5d orbital. These d orbitals are outer d orbitals. So these electrons are responsible for magnetism. So in case of transition series element, rather than saying the first transition series element, for transition series element, we find out of the spin and orbital contribution, there is no orbital contribution, only spin contribution remains. Then you will be the question, does it mean that electron is not orbiting, electron is not moving? It is not likewise. Electron is moving. It has to. It's a right. It's a fundamental tendency. It is property, wave nature. Hensberg uncertainty principle is there. So electron is moving, but we are not considering its movement because it is quenched or disturbed because of surrounding. Now I am discussing with you on your device, you are listening, but nearby any disturbances are there, then whatever I am talking may possible it is not clearly audible to you. I am not clearly audible to you because chaos or disturbances are there in your neighboring atmosphere or nearby. So those things are disturbing you. Likewise, electrons when remain outside, then those get disturbed. But if you remain to such a region, if you remain in such a place which is inside, disturbances are from outside, then you will be well protected. Means you are in your house, in the room inside, and surrounding there may be the obstacles or disturbances are there. Then inside region will not get disturbed. You will not get disturbed if you study inside. But you remain outside in the corridor or as such, then many other people will come or discussion will be there, some work may be there, and because of that, disturbances may be there. Likewise, our electrons also stay in the room or house. If electrons are inside, 1s electron, then say 2s electron, then 2p electron, then 3s electron, then 3p electron, and now we are talking about 3d electron. Now in this house, this 1s room is inside, 2s room is inside, but last room is outside, corridor. Then where will be the more chances of disturbance? Disturbance to surrounding, I'm saying. Now for atom also they remain surrounding, other atoms to surround. If any ion is in solution, ion is swimming in the solution, then solution is there, solvent molecules are there, they are surrounding. So which orbital is there? Which will experience disturbance?
3p.
3D is outer orbital. Yes, this 3D orbital will experience the disturbance. And that disturbance will be for what? The disturbance will be for this motion, this speed. And what is that speed? It is an orbital speed. Therefore, it is said for transition series element, while considering, calculating, or finding their magnetic properties, only spin motion contributes. Orbital motion does not contribute. Orbital vector does not contribute. So considering that spin, one formula is there. Before that, is that point clear to you? Though two types of motions are there for electron, spin and orbital, out of that only spin motion contributes for the magnetism, not orbital. Why not orbital motion contributes? Because it is gets quenched, it gets disturbed because of the surrounding. So it is there, but we could not understand that magnetism because of the surrounding. I am talking, you could able to listen, but you could not because surrounding. I like you will understand the disturbances of surrounding and the feeble sound, lesser sound. Likewise, because of surrounding, that speed or that motion gets quenched or disturbed. Which motion? Orbital motion. So magnetism for transition series element is solely, completely due to spin motion of the electron. Is this point clear?
Yes, sir.
Yes, sir.
Yes, sir.
Good. Now considering that spin motion, there is one formula. I write that formula first. It's a mu. Mu means magnetic momentum. Magnetism. That mu is equal to square root of n into n plus 2. And unit for that magnetism, magnetic moment, is Bm. If anybody knows, one can answer. I give time to you for answer. Let me express these terms. This mu is magnetic moment, or it is responsible for magnetism. If this mu is equal to 0, then that compound will be diamagnetic. If mu is greater than 0, then it can be paramagnetic or ferromagnetic, or you can say it is paramagnetic. When will it be 0? When value of n is equal to 0. I repeat, mu is a magnetic moment. It can be 0 or it can be positive. When it is 0, we say it is a diamagnetic. Further deep question I ask, when can this value be 0? When n will be 0. What is that n? N is number of what? Unpaired electrons. 1 unpaired electron, 2 unpaired electrons, 3, 4. How many unpaired electrons are there? That is n. If n is equal to 0, if we substitute here 0, 0 into 0 plus 2. Yes, what is the answer? 0 plus 2 means?
0.
0. Then what is 0 into 0? What is 0 into 0?
0.
Big 0.
0.
Yes, that's a magnetic moment, diamagnetic material. But when the number of unpaired electrons will be there, then magnetism will be there. Unpaired electron means spin will be there. But what we want here, we don't want spin, we want unpaired electron, number of unpaired electrons. Example, if there is a 1 unpaired electron, means n is equal to 1, then I write 1 into 1 plus 2. If I simplify that, square root of 1 into 3. What is the square root of 3? Answer. Yes, square root 2, root 3 is, as you might be knowing, no? 1.73. 1.73. And unit for that is this one. Yes. Will anybody answer what Bm means?
Bose magneton.
Good, brilliant. Bose magneton. Actually, when electron, its motion was considered, no, that Bohr has a considerable contribution for that concept to develop the atomic model. Theoretical failurities are there, but he has given the insight about the magnetism because of the unpaired electron. Though he is not perfect to explain the atom, but magnetism concept he could able to explain by means of the electron. So his name is given for the unit. That is what the Bohr magneton. If I have to sum up this page, the formula to find the magnetic momentum is mu is equal to square root of n into n plus 2, where mu means magnetic moment, where n means number of unpaired electron, and the magnetic moment can be 0, compound will be diamagnetic. When it will be 0, if it is a non-unpaired electron, and it can be positive, compound can be paramagnetic or ferromagnetic, means there are unpaired electron. For example, if I consider 1 unpaired electron, then magnetism will be 1.73. Let me continue this story. If I consider 2 unpaired electrons, then mu will be equal to square root of 2 into 2 plus 2. which is equal to square root of, yes, help me, final answer, square root of what will be there?
8.
Yes, which is equal to, yes, anybody can perform calculation and can give the answer. Square root of 9 means 3.
8284.
Yes, 2.84, right? No, yeah, 2.84, right? Yes or no? Or is different?
2.82.
82. Okay, okay, 2.82. Similarly, please calculate for 300 ton. Mu is equal to square root of 3 into 3 plus 2, which is equal to square root of 15, which is equal to, answer, square root of 15.
3.87.
One more, last, 400 ton.
4.90.
Now, hint I am giving that will help you to solve questions in JAM examination also. When one electron, 1.73, 200 on 2.82, 300 on 3.87, 400 on 4.90. So generally, it is not a fix. It depends on the complex. It depends upon the metal ion. But it is in nearby. 1.73 is exactly 1.73. No, it can be 1.58 also, or it can be 1.8 also. But nearby it will be there. When I'm talking about the transition elements and their compounds. If magnetic moment is 2.58, then you have to understand it is near to this. Means how many electrons will be there in that complex? 2 electrons will be there. Then for the 2 electron, what can be the oxidation state, or what can be the electronic configuration, or what will the strength of the ligand, that you can want the find out. So on the basis of the knowledge of magnetism, you can answer the questions regarding color, you can answer the questions regarding the stability also. That slowly stability concept you will understand, but electronic configuration will be clear because of the magnetism. Because sometimes what happens, low spin complexes, high spin complexes, means less number of electron, more number of electron. So how many electrons are there? Accordingly, you will come to know what kind of complex it is. Will be more stable or less stable. So stability, color, magnetism, and further property explanation, for that this concept is very, very important. Therefore, VBT, we give the importance to the VBT that we are discussing, because it could be able to explain magnetism. Not perfectly for all, but at least inside it has what the given. So theories have come on the basis of this magnetism concept. Conclusion is, if one electron, then 1 plus something, 200 electron, 2 plus something, 300 electron, 3 plus something, 400 electron, 4 plus something, those many magnetons or those many Bohr magnetons remain in that what the compound, or that magnetism remain for that the compound. So on the basis of magnetism, we can find out unpaired electrons. That's the importance of this concept. So if any complex is given to you, reverse way also we can go. Complex is given to you, you know its oxidation state of central metal ion, you know its electronic configuration. From that you can find out its magnetism. So reverse way also we can apply this concept. I repeat, this screen, this which are the on board writing is there that I am explaining. I had given you one formula. Yes. What was that formula? Mu is equal to? Yes, repeat. Mu is equal to
N
square root
plus
of? Yes, n plus 2 Bohr magneton. It is a formula that we accepted. It's spin only formula. N is the number of unpaired electron. And with the help of that, we did calculation. For one unpaired electron, how many magnetism will be there? For 2, 3, 4, likewise, did calculation. Conclusion is how many unpaired electrons are there? Nearly that much. That unpaired electron plus something will be the magnetism, magnetic moment for that the compound. Reverse way, knowing the magnetism, we can find out the number of the unpaired electrons. And those unpaired electrons will help us to understand electronic configuration, will help us to understand the color, will help us to understand the various properties. That's the importance of this magnetism concept. Other way, if we know one formula, if we know the metal ion, if we know the charge, if we know the number of electrons, we can predict its magnetism. So both way, the same formula, mu is equal to square root of n into n plus 2, we need to apply. Is this portion clear?
Yes, sir.
Yes, sir. Yes, sir.
Yes, sir.
Now let me take few examples and you will help me to calculate the magnetism. A complex means whether it will be paramagnetic or diamagnetic, that we can find out, and approximately what can be this magnetic moment that we can find out. Copper a co-complex. Copper is in dipositive oxidation state. Copper 2 complex I am considered. So just add your answer. Which metal ion is present in this complex?
Copper 2 plus.
Yes, copper plus 2. It's a rough idea I'm giving. Actually, a hybridization concept, when we learn, then further understanding will be there. Copper plus 2 means what is its electronic configuration? Copper atomic number 29. Outer electronic configuration you consider as orgon. After orgon, you consider electron in one orbital, electron in what other orbital. Which are those orbitals? Electron in 3D. How many you consider? 10. Electron 4s, you consider 1. I am talking about copper plus 2 ion. Then in such cases, what will the electronic configuration? Electron from 4s will go, and electron in 3D will be only 9 now. So electronic configuration for copper plus 2 is 3d9. So roughly, it's not a perfect concept. D orbital if I consider, then how electrons I can represent? First electron, second electron, third electron, fourth electron, fifth electron, sixth, seventh, eighth, ninth. So what is there? Is there an electron?
Yes, sir.
Yes, sir.
Because of this electron, what will you predict? This complex will be paramagnetic or diamagnetic?
Paramagnetic.
Paramagnetic.
Paramagnetic. It's a application of today's learning. But up to what extent? What exactly the magnetic moment is? That mu is equal to square root of 1 into 1 plus 2, which is equal to 1.73 Bohr. It's an approximate prediction. That quantitatively, qualitatively also you can say it's a paramagnetic or diamagnetic, and quantitatively also you can answer what can be its magnetic moment. Is this example clear?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
I want to talk about Mn plus 7. What do you think? Mn plus 7, paramagnetic or diamagnetic? Stepwise, let us go. Yes, electronic configuration, of course, electron will be in 3D orbital and 4s orbital, if they are there. Electronic configuration,
3d5 4s2.
it is for manganese, it is for Mn. Absolutely right. It is outer electron configuration. But my question is Mn plus 7. Plus 7. 7 electrons are removed. Remove 7 electrons and tell me
0. 0.
3D0.
3d0, 4s0. How many electrons are there?
0.
0.
What will be the magnetic moment?
Diamagnetic.
Diamagnetic.
Diamagnetic calculation, value. Diamagnetic, paramagnetic, qualitative answer. I want quantitative answer here. Mu is equal to big
0.
Big zero, yes. Zero Bohr magneton, and whatever you said, absolutely right. It will be diamagnetic in nature. Chromium plus 3. Predict its magnetism.
Paramagnetic.
Paramagnetic.
Okay. Final answer is paramagnetic, as you are saying. One by one. Electronic configuration, tell me. Chromium plus 3. Directly you have to go to chromium plus 3 because chromium we have discussed. I want chromium plus 3 now. Is my question clear?
Repeat, sir.
Electronic configuration for chromium plus 3.
3D3.
Right. So in those d orbitals, so we consider, so for 5d orbitals, how many electrons will be there in the d orbitals? Only 3. First electron, second and third. Whatever explanation now I am giving is a rough explanation. Later on, one theory came to explain all those. That theory is called valence bond theory. That also is included in your syllabus. So here, how many unpaired electrons are there?
3.
3.
Yes. Because of that, it will be paramagnetic. It is a qualitative answer, but I want quantitative answer. Now tell me, what will be its magnetic moment? Approximately.
3.87.
Good. It's approximately. Means 3 and more number will be there. It is expected. If complex changes, it varies. But at least good idea we got. What's the conclusion from this? Whatever our assumption is there, whatever we consider spin only formula is right. Only spin, orbital motion we have not considered. Next year, you will come across few elements and the compounds where along with spin motion, we have to consider orbital motion. So along with one vector, this is one vector, say it's a spin vector. Along with the other vector, that is a L vector, S bar and L bar. If such two vectors are there, vector means the direction will be there, and direction need not to be the same, perfectly same or perfectly opposite. Perfectly same means double, or addition will be there, perfectly opposite means subtraction will be there, likewise you know. But suppose if any particular angle is there into two vectors, then one law is there. With the help of that, we find resultant vector. What is that law? In 11th standard you might have studied law of dash. To find resultant vector, it's a one vector, it's a second vector. To find result vector, one law is there. What is that law? Law of, hint I give it to you. Anybody can guess?
Parallelogram.
Right. Brilliant, brilliant. Parallelogram. So parallelogram you have to complete. So what I have to do? I have to draw a parallel line here, parallel to L bar, and similarly parallel to S bar. So whatever the result will be there, that's a diagonal element. That is what the our result. It is resultant vector. So its direction and its magnitude. It is not exactly to L bar and it is not exactly to S bar. So law of parallelogram, with that we can find out resultant vector, and that we represent as J, coupling constant, coupling parameter, that you will come to know next year perfectly. And with the help of that, we can find out the magnetism, we can describe the magnetism. Here only spin formula is coming for our help. Is this explanation clear?
Yes, sir.
Yes, sir.
Let us revise today's learning, and then one more example that I'll give to you and I want answer from. We know magnetism is due to the electron because electron itself is a tiny magnet, and electron has two types of speeds which are responsible for the magnetism. One is spin, another is orbital. But out of those two, only one speed we consider, only one speed we take care, and that's spin motion. Why only one speed? Why not orbital? Because orbital motion or orbital speed is quenched or disturbed. It is there, but we do not understand that because of the disturbances. We don't realize that. But spin speed has the contribution. Therefore, we concluded one formula to find out the magnetic momentum. Mu is equal to square root of n into n plus 2 Bohr magneton, where n is a number of unpaired electrons. Qualitatively and quantitatively we can give the answer. So various ions I discuss. If one unpaired electron, then magnetic moment will be 1 and something, 2, then 2 and something, 3 and 3 and something. If we know practical data, practically we can measure the magnetic moment. On the basis of that, we can find what can be the electronic configuration of the metal ion in that compound. Is this portion clear?
Yes, sir.
Yes, sir.
Yes. Now, I tell you practical approach, how to find, how to measure magnetic moment, means how people or scientists think and devise the instrument to measure the magnetic moment that I discuss. It is measured by many ways are there, but one of the way is one balance that is called as Gauss balance. Now, you know balance, electronic balance about which you are aware, but at that time, pan balances were there. Pan balances, now also pan remain, but two pan balances were there. I'm talking about the old days. Now also, if you go in the grocery shop, there will be the two pans. In one pan, there will be the weight, and other pan, the material which you want to weigh will be there. So two pan balance. Do you know that two pan balance?
Yes, sir.
Yeah. So here in that one thing will be there. So it's a one pan. And by the way, other pan also remain. Okay. Don't go on my diagram. Okay. And it is what? One bar. That's arm remains. Okay. Suppose if anything goes down, then which here pointer remains, no? That pointer will get deflected. So with that we can here similar balance is used in that Gauss balance concept. But magnetism is there. So experimental setup I informed to you, and then you will understand the remaining things. In that Gauss balance, there remains horseshoe magnet or strong magnetic field. So that magnetic field, magnets I represent here. Two magnets are there. Two strong magnets are there. Means those are causing the magnetic field. Likewise, magnetic field is there. Or remove that magnetic field now, but magnetic field is there. And our material, suppose if our material is liquid, compound is liquid, then we can take in one capillary or fusion tube. Fusion tube for organic chemistry, you might be knowing, a small tube, or you can consider test tube. In the test tube, we can keep the compound if it is a liquid. If it is a not liquid, then we can keep in any pouch also and we can bring it down. Yes, are you understanding what I'm saying?
Yes, sir.
Yeah. So this is the one. Here the liquid test tube is considered, and it is linked to, just I remove this previous things. It is linked to, it work as a one pan, and there remains a other pan. As usual, I represent the pan in this way. And in other pan, there remains a weights. So before putting it, means once this magnetic moment, north and south by concept, is magnetic moment, magnetic field, to make it on, those remains electromagnets. Then we will weigh that. Say that weight is W1. What is that weight? Weight before magnetism or before magnetic field, before bringing the material in magnetic field. So simple weight. That's a first. That's a W1. Two possibilities are there. This material can be this here can be paramagnetic or it can be diamagnetic. Answer for my question. If it is a paramagnetic, then it will be attracted towards magnetic field or it will be repelled.
Attracted.
Attracted. So that tube or capillary or this container will feel something is there in magnetic field. It is pulling that content down. It will bring it down. So indirectly, its motion will be like down. Something is pulling that. Because of that pulling, the weight of that material will increase or will decrease. Something is there inside and you're weighing that. But I'm pulling that and you're weighing that now. Weight will increase or decrease. Balance is here. Here you can consider the central portion. Arrow is there. It will move to right side or it will move to left side. It's a question. Means weight will increase or decrease?
Increase.
All right. Any other answer? Increase. Somebody is pulling, no? Increase. But suppose there is a repulsion. This compound is diamagnetic. So to that capillary, to that tube, somebody is pushing up. Then what this balance will understand? Weight will decrease or increase?
Decrease.
Weight will increase. Yes. There we can conclude whether the compound is paramagnetic or diamagnetic. So what are we doing? We are measuring the weight before magnetism, before bringing the compound in magnetic field. Then we are measuring it in presence of magnetic field. Say that weight is W2. It is after magnetic field. If W2 is less than W1, what will you say? Paramagnetic or diamagnetic? In presence of magnetic field, weight is less. Paramagnetic or diamagnetic?
Diamagnetic.
Yes. And if W2 is greater than W1, the compound will be paramagnetic.
Paramagnetic.
Yes. So it's a qualitative answer. But by how much amount it decreases and by how much amount it increases, based on that, we can find magnetic moment. Are you getting this point?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
If there is a decrease, then certainly diamagnetism. So there is repulsion. But when there is increase, no. So how much increase? How many lines are passing? That much attraction will be there. That much increase in weight will be there. And as more increase in the weight, more number of unpaid electrons will be there. So there is the formula with which we can find out the magnetism. That direct answer you get, and from that you have to find out unpaid electron, or you know electronic configuration. From that you have to guess the magnetic property or magnetic moment. So experimental device or how experimentally magnetism is measured, that I informed to you. So depending upon increase, how much increase they will understand. To make this concept clear, see, when we fetch a water from the well or container, we put it in the well. That's a water pool. Then as that container remains in the water, we feel one kind of weight. But as we fetch it up, as that container comes up, as it comes above the water, you will feel other weight. Are you understanding what I'm saying?
Yes, sir.
Yes, sir.
Yes. Now answer for my question. When that container remains in the well water, deep in the well water, that weight remains less or more?
More.
In water.
More.
Less.
Oh, I'm not understanding. Have you fetched the water?
Less.
See, as that container comes up from the water, actually container is filled with the water. Filled container with water is in the deep water, and you are pulling. In water session, you will find it's very light. Are you following?
Yes, sir.
It's easy.
sir.
As it comes up, more power, more work you have to do. Means it becomes heavy. Actually, it's as it is. In water, it becomes lighter. Are you understanding? Could you cope up with my discussion?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Why there is a less weight in water? In that water pool, there is a less weight. Why? Because of one phenomenon that is called as, yes, it is called as F.Y.B.Sc phenomenon. There is an upward thrust, pull will be there. From outside also there will be so because of that net weight we find the less in the water. Any medium if you put then every medium remains with a different buoyancy. So different weight will be the experienced. Yes, is it clear to you?
Yes, sir.
Yes, sir.
Sir.
Yes. Now last example that we'll take and we'll stop our discussion. Example is cobalt plus 3. Yes, help me. Electronic configuration.
3d6.
Brilliant. So here both possibilities are there. It can be paramagnetic or diamagnetic. But as your general way, as per now today's your understanding, what will you say? Paramagnetic or diamagnetic?
Paramagnetic.
Yes, brilliant. So our today's discussion, whatever I want to discuss is over. Yes, could you able to see the screen what I'm writing now?
Yes, sir.
Yes,
Yes,
sir.
yes, yes. Everything is going on. So I stop the presentation. Shall we stop now?
Yes, sir.
Yes, sir. Yeah. Tomorrow, I'll be in the journey, but I'll conduct lecture. Maybe little delay will be there, but I'll inform you. I'll be in communication. Probably at 12:30 our lecture is there. I'll what the start. This is what the no issue. So further aspects are there, concepts are there. We will discuss as per usual aspect, revision, and the new concept we will what the discuss. So shall I stop now?
Yes, sir.
Yes, sir.